All right, so question, is your pulse rate different when you take a quiz than when you take a regular class? Test the claim that a student's pulse rate is not significantly different when taking a quiz than attending a regular class. The mean pulse rate difference is 2.7 with a standard deviation of 9.93 out of 10 students uses a significance level of 0.5%, 0.005. So a couple things I'm going to add to this. There's been some confusion as I've been grading activity, no, what do they call them? Application 6 on the confidence interval for the, what was that one? The effectiveness time, mean effectiveness time of a tranquilizer. And what's the difference between a population and a sample? So here we're given a sample. The question is, what is the population? So I'm just going to make some general notes on what's going on here. What population are we sampling from? I would say this is all students who take quizzes. And if I look up the data that they pulled here, this is most likely college students. So I'm going to amend this population a little bit. Okay, so the population is all college students who take quizzes, which is pretty much all college students. That's a lot of people. We can't easily find them all. Some of them have graduated and some of them are yet to be. So population's a huge thing. What's the parameter here? Welcome, Deanna. Welcome, Eskar. The parameter here is, let's see, we have a difference in pulse rate, quiz minus lecture. And then we are measuring the average. So we have a parameter of average difference. Of let's see, pulse rate, yep. And the difference, we should make a note, is the pulse rate when they're taking the quiz minus the pulse rate when they're in lecture. And this is an average of the differences, not a difference of the averages, and that is a big distinction. It's the order of operations that matters. First, we find a person. We measure their pulse rate in lecture. We measure their pulse rate in a quiz. We take the quiz pulse rate, we subtract the lecture pulse rate, and we get a number. And we do that for lots and lots of students. Now here we only have 10. We'd probably like to have more than that. And again, we're doing this for a population of all. Okay. So that's my parameter. My parameter is a mu in this case, right? A mean, an average. So I'm going to put a little mu over here. And then we have the sample. Sample. These 10 students. Hopefully it's a good random sample. And then we have the statistic. The statistic in this case is the average difference of their pulse rates. And that would be an X bar. And we've already been given that if we add these up and divide by 10, we're going to get 2.7. So on average, this group of 10 students, their pulse rate was slightly higher on a quiz. They have a difference of positive 2.7, quiz minus lecture. So a slightly higher pulse rate on a quiz on average. Now notice some people had a lower pulse rate when they took their quiz. Some people had a much higher. There's a wide range of numbers for the actual individuals. When we look at the sampling distribution and say a confidence interval, that's going to be always much narrower because we're looking at an average. And again, I'm going over this because there was a lot of confusion on application 6 about what's a population and what's a sample. and those two are mixed up for majority of the class. All right, so we want to run a hypothesis test here. So the question is, what test are we running? What's our null hypothesis? What's our alternative hypothesis? So we got to come up with a null hypothesis. We have to come up with an alternative hypothesis. And in this case, it's for a mean. So I'm going to have a mu here and a mu here. And then what am I given? Test the claim that a student's pulse rate is not significantly different. Okay, so if they're the same, so let's kind of sketch this out. If the pulse rate's the same, that means when we take the quiz rate and we subtract the lecture rate, then that's going to give us a 0. If they're different, that would imply when we take the quiz and we subtract the lecture that it's not 0, right? They're two different numbers. And so here the claim is that they are not different, so that's the same. Not different means the same, so that's an equal to, so my null hypothesis has to be that equal to. And the alternative, since there's no mention of greater or less, is going to have to be not equal to, right? It doesn't say here, test to claim that the pulse rate's higher on a quiz. It doesn't say test to claim that the pulse rate's lower on a quiz. It just says that they're not different. Not different means the same means the difference is 0. So that's a tough one to reason through. And again, the only choice we have, because we have nothing else to go on, is that they are not 0 for the alternative. So that means this is a two-tail test, which is a little trickier. All right, so right away, this was a tough problem. Now we're ready to, and again, this is important. Don't run the test until you're sure of your definitions. What are you talking about here? What's your null? What's your alternative? And I'm going to start my sketch before I run this. So new page, let's switch colors. So throw down your x-axis, make your best bell-shaped curve. Ooh, it's a wiggly one. Mark either your mean or your proportion in the middle. So we have mu is 0. So 0 means they're not different, they're the same. And our alternative is they're not. So that means we could have data out here or we could have data out here. This is a two-tailed test. And again, what am I measuring? We are measuring the mean difference. Difference here is quiz minus lecture. So I can't emphasize enough how it's important to take notes when you do these. Mean difference of pulse rate. And again, my null, mu is 0, and the alternative, average difference, it's my mu, is not 0. So that right there, not 0, means it could be left, could be right, two-tailed test. So we're going to have to reflect on both sides here for this. So we found in the sample, x bar was 2.7, and the question is 2.7 relatively close to 0 or is it far from 0? And deciding what close means is always a tricky thing. We were told that close is related to that 0.005, which is 0.5%. Since we have two tails, we have to split that. So we're going to consider alpha over 2, which would be 0.25%, so 1/4%. Okay, so we can have it. So our sample has to be out in the way right fringe or way left fringe of the distribution of sample means. See where we fall. I don't think 2.7 is very far from 0 is my guess, which means we're going to fail to reject. And then we'll write our conclusion. So we need StatKey. There's probably a link here somewhere. Yep. All right. Oop, I already answered this one. So let's regen. So the answers aren't there. All right, so it is a mu equal to versus not equal to. So that's the right one there. Because it's a not equal to, that implies two tails. We have to examine, and then we jump in and find the p-value. Switch data sets. So always make sure you have the right data set. And this one is already in here somewhere. There you go, pulse rate difference. And if we double check the data table, that's the same data that I gave you on the page. And mu is set to 0. Always double check your data, double check your mu before you continue. Here's that mean of 2.7 in the sample of 10. And now we just generate thousands of samples of 10 students each. So remember, every one of these dots represents a different group of 10 students, kind of based on the original one. And they have a slightly different mean difference. So this group of 10 students, they have an average pulse rate of negative 2.3. So that means what, they were calmer during the quiz than the lecture. And these guys over here, mean of 5.4, listed at the bottom down there, means they had a slightly higher pulse rate during the test or the quiz. All right, so again, we've run, let's say I only have 1,000, we need at least 6,000 to get a legitimate sampling distribution. And again, what is a sampling distribution? It is a graph of a whole bunch of means. Every mean is from another sample of 10 students. So I have 8,000 groups of 10 students, and all I'm plotting is the average of those 10 students. Whenever you plot an average as opposed to the original data, you're going to get a much narrower spread. Notice that my original sample has a spread of about negative 20 to 20, but the sampling distribution has a spread of about negative 10 to 10. Right, because we're looking at the average. If you look at the average, that means you've factored it. The min and the max are now like condensed into that one middle number. So anytime you do averages, you condense the data. All right, two-tailed test. Let's get on with this. And then we plug in our data, and again, plug it in on the right side. That number is above my mean, so that means I'm going to go to this side and enter the 2.7 mean of the sample. StatKey is going to automatically reflect it to the other side. The number won't always match, but it'll be close. All right, so that's close, but on the other side. And so what this is telling me here, that the probability of getting another sample where the pulse rate is more than 2.7 to the right or more than 2.6 to the left is 0.188 plus 0.188. For a two-tailed test, we have to add up both probabilities on each side. So let's copy that screenshot. New page, please. All right, so let's mark this up a little bit. Sorry, I got part of the Zoom window in there. All right, so in this case, since it's a two-tailed test, the p-value is the sum of the probabilities on each side. So this is the proportion of samples that were more extreme to the left. This is the proportion of samples that were more extreme to the right. And we need both of those for the p-value of a two-tailed test. So my p-value is 0.188 plus 0.188. Calculator, double check your arithmetic. So I get a p-value of about 37.6%. I don't know, I'm rewriting that. All right, so that's my p-value right there. Let's highlight you. And because the simulation's different every time, because it's a randomization, it's not theoretical like flipping a coin. You think it's 1/2, but you won't always get exactly 1/2 heads. If I reset the plot and do this again, I'll probably get slightly different numbers. Notice it's a little more skewed right than the previous one. Two-tail, let's go up to 8,000 just like before. Set the mean. So remember, you got to double check you have the right data, double check you got the right mean, and then generate samples, pick the right test to do, and then plug in your sample data to get the p-value. And that procedure is written up in a page further back. Another request for number 13, cool. So now notice it's a little bit different. This time it's 0.183 plus 0.183. So I'm getting slightly different p-values, but they're in the ballpark of each other. They're around the same. So I'm just going to make a note here. Another simulation gave me a p-value of 3. What would that be, 66? Oops, no, my decimal's in the wrong spot. 0.366 was the other one. So it's pretty close to this one, but it'll vary. All right, so what does that mean? Oh, good question. That's pretty damn big probability, 30%, right? I might bet on that. So what that means is the sample is pretty close to the null hypothesis. It supports the null hypothesis. So our decision here is to fail to reject the null hypothesis. Conclusion is a little more wordy thing than that. So let's write up a conclusion before we go to that homework page. And even if it doesn't ask for a conclusion, I would highly recommend practicing writing conclusions because I am going to ask you to write some conclusions on the final exam and on the application. So the conclusion here is there is not sufficient evidence to reject the claim or hypothesis and hang on, I'm going to move my Zoom tools out of the way. That the average difference and I'll make a note again, that is, oops, quiz minus lecture in pulse rates let's see, is not different. Double check I got the wording right. Let's see, back here I was thinking about that. So if it's different, then we should not get 0, but we got it's close enough. So yeah, so not different is not different. Okay. So that 2.7 is close enough to 0 to say it's close enough to 0. We think that on average, most people aren't much more elevated in their pulse rate on a quiz than in lecture. On average, individuals will vary greatly, but we're talking about the average here, not an individual. All right, back to homework. And so in this case, I asked for your p-value, mine was 376. Hopefully that's close enough to what the computer was expecting, and I'm failing to reject the null hypothesis. It didn't ask for a conclusion, but again, you should always practice writing those. And sometimes your simulation, it might be too different, just too weird resampling. I liked either one. So if you happen to get a p-value and you think you did it right that the computer doesn't like, try resetting and running it again and try the new number you get. And if the computer doesn't like it, but you think you're right, then send me a note with some information about what you tried and what your results were, and I'll double check it for you. Okay, any other questions on this one? Mindy, I think you asked about it. Does that clarify a bit? This is a tough one. Okay. Can you see the drawing? Yeah. Oh yeah, I didn't finish updating my drawing. Let's do that. All right. So based on the stat key, I then go back and update my hand-drawn picture here. So 2.7 was here. Theoretically, this should have been a negative 2.7, but let's see, what did StatKey say the second time? Curious. Let's see. The first time it said negative 2.6 on that side. See, I don't have quite enough yet, and I deleted it. Two-tail, 2.7. Yeah, it said about the same, negative 2.6 on the other side, because there's a slight skew to the data, and that's okay. So here, this was my actual data, and then I'm going to label this x value negative 2.6, and then this group over here and that group over there for me was, let's see, it was 0.188 on this side and 0.188 on that side. So my p-value is the sum of those. So this is my more complete picture. And so what I'm expecting, again, to see in your picture is you label either mu or p and whatever that number is in the middle, and then you label your sample data, which is your proportion from the sample, or in this case, your mean from the sample, right tail or left tail, and two tails, you have to label both sides. So each time you do one of these problems, I do recommend you write up a page like this here that says, what are you measuring? That shows this graph here. Label the null hypothesis in the middle, label your sample data on one side, the other, or both, depending on the test. State your hypotheses. And again, my p-value is way bigger than my significance level, which is another reason we say reject. Or fail to reject, sorry. All right, I'm going to stop this recording and start a new one for the next problem.